Hello everyone, my name is Paszke, and I want to present to you a joint work with Michał Pilipczuk, which concerns the VC density of set-like systems that are definable in tree-like graphs. So before we get into it, let's define what the VC parameters actually are. So they're all based around the concept of a growth function, and the growth function for a set system, where a set system is just some universe of elements and a family of subsets of that universe, basically for each integer n, it basically is the quantity which is something as following. We look at all of the subsets of the universe that are of size equal exactly to n, and we look at how many subsets of that particular subset of the universe we can actually form by taking the intersections with all of the sets from the sort of set family S. And then the VC dimension, which is sort of the core parameter of the theory, is exactly the largest natural number for which this particular function is equal to 2 to n, right? 2 to n is a trivial upper bound for this because you can never form more subsets of an n-element set. But if such a bound exists, then we say that the set family has actually a bounded VC dimension. And then most applications of VC dimension actually go through the Zauer-Gela lemma, which says something like this. If your set system actually has a VC dimension that is bounded by D, then the growth function actually can be bounded by such a truncated sum of binomial coefficients, which essentially gives you an asymptotically polynomial bound with the VC dimension in the exponent for the growth function. And that is very useful for a lot of applications. But it turns out that actually the Zauer-Gela lemma might give you some particularly poor bounds for those exponents. And so in some more modern literature, you often find the introduction of a parameter that is called the VC density. And what it is exactly this. It is the smallest real number, which is the exponent of, for some C, essentially we try to bound the growth function by a polynomial function with the exponent of alpha. And we look over all coefficients and we just pick the smallest one for which we can obtain such a bound. And those are usually much, much tighter than whatever you get from the Zauer-Gela lemma. Now, sort of the working sort of application that we will be talking about in this particular presentation is set covering in graphs. And so what I mean by this is, well, set cover is this general problem where you get, again, a universe of some elements and some family of subsets of this universe. And the idea is that you want to find the smallest subfamily such that when you take its union, you still get it equals to the whole universe, right? So you want to cover the universe with as few sets from the family as you can. And when I say in graphs, what I mean by this is that the sort of set family that we will be working with will be somehow derived from the structure of the graph. And so one very simple such a problem is called vertex cover, and it's pretty popular. So what vertex cover is for each vertex, you look at its immediate neighborhood. So for example, A, the immediate neighborhood looks somewhat like this. For H, the immediate neighborhood looks somewhat like this. And so you gather all of those neighborhoods of those vertices into a single family, and then you want to pick sort of the smallest subfamily such that the whole graph is covered, right? That is essentially what the vertex cover problem is. It's like a very well-researched problem at this point. But, vertex cover is somewhat specific, right? We always look at the immediate neighborhoods, and the question is like, what if we try to generalize this somehow, right? What if we looked at neighborhoods, let's say, at distance r, at some fixed distance r, or maybe we wanted to say that we look at vertices that are at distance at most 2, but only of vertices that have a degree at least 2, right? So not every single vertex, but only those that have a high enough degree. And once we sort of start talking about constraints like this, the natural language to actually formalize those constraints is a language of logic, right? So now we will be dealing with like defining set systems in graphs through logical formulas. So what we do is all of our formulas will have sort of two groups of variables. One will be the object variables and one will be the parameter variables. And so the way we will form the set system is we will iterate over all vertices in our graph for those parameter variables, and for each such setting of the parameters, in this case we just have one, so this will be a single vertex, right? For each single setting of those parameters, we will again iterate over all, we will add a set to our set family, and the contents of this set will be determined by all of these sort of all of the sort of valuations of the object variables for which this formula is satisfied with those given parameters, right? So for example, if we set y to be equal to a, then actually we will only add an empty set to our family, and that is because this sort of constraint in here says that the vertex, the parameter vertex that we're considering has to be of degree at least 2, and a only has a degree equal to 1. But if, for example, we look at a vertex such as f, then well, if we look at the vertices that satisfy it, then like our neighborhood will look somewhat like this, right? Remember that now we're not only looking at the immediate neighborhoods, but also at neighborhoods at distance 2. So actually our set will look somewhat like this, right? So you can see that those sets get larger, but in this particular graph, not all vertices will get their sets added to the family because some of them will be empty. Like for example, for A, C, and G, those sets will actually be empty. And what is interesting is that actually this phenomenon can be even further generalized. If you take a look at sparse graphs, in this case we will be talking about graphs of bounded expansion, although the full definition of this notion is completely out of scope of this talk, is that there is actually a theorem such that says that, well, for every single formula, which is a partitioned, because we want to form this set family, first order logic formula, if we have a class of graphs which has a bounded expansion, then basically the VC density of the system that is defined by phi in this particular class has to be bounded by just the number of parameter variables, right? And that is actually a very strong bound. Like there are no constants involved, nothing, right? In particular, like if you have just a single parameter variable, then the VC density is just 1. And actually one cannot expect to do better than that. And the proof of this is just this trivial formula which allows you to basically select arbitrary sort of subset of the arbitrary number of subsets of the universe of the like graph sets of vertices of the graph of size equal to the number of parameters. So this is a somewhat optimal upper bound for this particular class of graphs. And why this is interesting is that, as I've mentioned, so if you have only a single parameter, then your VC density is equal to 1, so it is bounded by a linear function. And what this says is that, well, because we can define the set family of neighborhoods at distance r from each vertex, right? From each vertex is the key word here. We only need a single parameter. We get a graph. We get a set family of linear VC density. And if we just connect this with another theorem, which basically says that, well, if your family has a linear VC density, then actually the weighted set cover, so we no longer look for the smallest sort of subfamily that covers the set, we look for the family of the subfamily of the smallest weight totally. It actually admits constant factor approximation on such sets, right? And what this means is that, for example, the weighted dominating set, so this is somewhat like vertex cover, the weighted dominating set at distance r problem admits a constant factor approximation algorithm in bounded expansion classes. This is a result that sort of was not well known until just some time ago. So then what's interesting is that there's actually also a dual theorem, which says that, well, if actually we have a graph class which does not have bounded expansion now, right? So it is not sparse according to this notion, and it is actually closed under taking subgraphs, then there is a counterexample, right? It cannot have sort of low VC density. There is actually a first order logic formula with just a single parameter that defines a system of superlinear VC density, right? That could not happen under the previous theorem. So basically this means that when we consider subgraph closed classes of graphs, only bounded expansion classes actually have good sort of properties when it comes to defining set systems using logical formulas, right? But then there are some natural questions that arise, right? Like, what if we considered more powerful logics, right? What if we considered, we will basically discuss some of those. And also, what if we considered dense graphs? So let's go over a few popular logics that are used in the context of graphs. So the one that we've already seen is first order logic, right? And so what happens here is that we have a domain that's built of vertices, and we have a binary edge relation. And we can quantify over those vertices, of course, nothing special happens there. Now the interesting generalizations that are often mentioned in computer science are monadic second order logic 1, usually abbreviated as just MSO1. What this means is that, well, the domain still consists of just vertices, but now the monadic part basically says that we can actually quantify over subsets of the domain. So we can also quantify over subsets of vertices, and we still only have the binary edge relation. Now there is, and then there is also monadic second order logic 2, usually abbreviated as MSO2, and then the domain actually consists of vertices and edges, which is the interesting thing, and we can quantify over subsets of those. So we can actually also start quantifying over subsets of edges. And then the counting MSO, which is usually abbreviated as, C MSO for some n, is the MSO n logic with the addition of a predicate that lets us sort of check the set sizes modulo some constants. So you essentially get like counting modulo something. And so then, the natural research question that we sort of already posed is that what are the largest graph classes where MSO1 definable or MSO2 definable set systems have also optimal VC density, right? So we again want to bound the VC density of those formulas just by the number of parameters that appear there. And the answers actually appear in related work partially, right? So if we take a class of graphs, C, right, and again, we take a partition formula phi, then if C has bounded clique-width, and so this is some kind of graph parameter, which we'll sort of briefly introduce in a second, and the formula is in the MSO1 logic, or C has bounded tree width, so that is another graph parameter which we'll introduce shortly, and phi is an MSO2 formula, then actually the VC dimension, so not density, the VC dimension of the system of the sets that are definable in C is bounded by a constant. So not exactly what we're looking for. This is not the tight bound on the density, right? Like in particular, the theorem only talk about VC dimension and not density, and the constants that are mentioned in the theorem are pretty huge. So if we just use the Zauer-Schella lemma, we would get something which is significantly worse than this bound, which we would normally obtain from the previous theorem. And so the question is, can we actually improve on this related work? But we already have some natural candidates, right? We have sort of bounded clique-width for MSO1 and bounded tree-width for MSO2. But also, like, those graph classes are actually often connected with those logics, so those would be natural candidates for this nevertheless. So when it comes to tree width and clique width, graphs of bounded tree width, they're always sparse, and basically the idea is that they have like a tree-like structure. The idea is that you can imagine that your graph is somewhat like a thick tree, right, where you can decompose it into a tree where like every tree contains some bounded, every tree node contains some bounded sort of size subgraph of your particular graph. In particular, graphs of tree width 1 are exactly just trees. Then clique width, those graphs are generally dense. We start allowing dense graphs, which is an interesting generalization compared to the previous results, but they still have a constraint in that they can be constructed from some smaller bounded clique-width graphs using some grammar of terms. So we sort of get trees, which are the syntax trees that show us how to build those dense graphs, right? So even though they're dense, they sort of still have a lot of vertices, which in some sense behave very similarly. In particular, graphs of clique-width 1 are cliques, right, which are, even though are dense, like all of the vertices are completely indistinguishable from each other. So you can also expect that the logical formulas will not be able to like define extremely complex set systems because everything sort of looks kind of similar. All right, so let's move on to our results. We've shown basically what we wanted to show. If we have a class of graphs and we have a partition formula, then basically if this class has bounded clique width, and the formula is in CMSO1, so this is slightly general than the previous sort of related work result that I've shown you, although the generalization is somewhat straightforward, or C has bounded tree width and the formula is in CMSO2, then the VC density now of the system that, of the definable sets by phi, so the set systems that are defined by phi in C, is just bounded by the number of parameters of the formula phi. So again, we get this really nice, really simple and really powerful bound. Correspondingly, we also get the lower bounds, right? So now, instead of just saying that the graphs are subgraph closed, because that does not really make sense, for example, in the context of clique width, right? If you assume that a class even of clique width bounded by 1 is subgraph closed, then you get a class of all graphs because you get because the original class contained all the cliques, right? So that is not an interesting notion. So we had to sort of pick a slightly different formulation of this. So what do we say now is that, well, if there exists a finite label set, and if we have a class of graphs that are labeled by that particular label set lambda, and the assumption here is that every particular sort of coloring of the graph using that labels is in the class, and then we define L to be some logic, and so if C contains graphs that have arbitrary large clique widths, and the logic that we need to sort of show our counterexample is C to MSO1, or C contains graphs of arbitrary large tree width, and the logic is just MSO2, then we can define a formula phi in each of those corresponding logics that defines set systems of arbitrary high VC dimension in that particular class, right? In particular, having unbounded VC dimension means that you cannot have a bounded VC density by the Zauersche-Lie lemma. All right, let's take a look at how we could actually prove such upper bounds. So the idea here is that both graphs of bounded tree width and graphs of bounded clique width are interpretable in trees. And so what this means is that if you have labeled trees, then like using logic, you can sort of pretend that you don't have the original graph, but you can sort of get the structure of the original graph just by applying sort of a complex logical formula on that particular labeled tree. And so this basically allows us to just focus on the case of trees. And then another important piece of information is that, well, MSO or like CMSO formulas over trees actually correspond to tree automata. So what tree automata are very simple sort of decision procedures where you pick, based on the sort of label of every leaf, you pick the state of the automata in that leaf. And then for every internal node, you basically look at the state of the left child, you look at the state of the right child, and you look at the label of your particular node. And based on this, you pick a state for that inner node, right? And so you do this bottom-up traversal of the tree, and then you look at the state that is in the root, and if this is one of the accepting states, then you sort of accept the tree. And how this extends to formulas with free variables is that, well, we extend the labeling of the tree with an alphabet of sort of binary markers. We'll add a binary marker for each variable of that appears in X, and a binary marker for each variable that appears in Y. And the idea is that once we get a formula with some valuation of those variables X and Y, then we will set the binary markers to 1 exactly in the nodes that are selected as each variable, right? And so this way sort of the automaton can like actually read out the valuation of the variables from the individual nodes of the tree, and you can show, and this has been shown previously in related work, that this exactly corresponds to running MSO to sort of evaluating MSO formulas on those particular trees. Okay, and when it comes to our actual proof, the idea here is that, well, we have a tree, right, some label of tree, and we have some subset of A. We are interested in sort of bounding the growth function, and so we will want to show that you can only sort of, using sort of parameters from the whole tree, you can only select like a small number of subsets of that particular set A in that tree, right? And so what we will do is we will enlarge the set A to a set called B, basically by selecting nodes according to the following rule. We always take the root of the tree, and then we also take every node such that there is some descendant of that node which is in A on the right-hand side, in the right subtree, and there is some descendant of this node which is in A in the left subtree, right? So sort of all like join points of the paths from the vertices of A to the tree root. So you can actually show that this procedure does not enlarge the set A too much. In fact, the set B can be at most twice as large as the set A. And then the idea is that we sort of look at all subtrees, right? We sort of, for every vertex of A, we sort of look at the whole subtree. And for this, and we always stop once we encounter like another vertex of which is in B. So this guy in here is just a subtree alone. This guy in here, we look at the whole subtree, but we sort of stop looking once we encounter like this vertex of A. So we take this subtree, then this vertex of B. We go here. We can't go left because, well, there's this guy in A or in B, and then we sort of only take this, right? So hopefully you sort of understand the sketch of the procedure. And given this, we sort of get some kind of a partitioning of the tree, and this allows us to collapse this whole big tree into a small tree, which only contains essentially at least 2 times size of A nodes, right? And so it is pretty small. And then sort of the bulk of the proof is just showing that you can accurately simulate the runs of an automaton on this large original tree in this small tree just by sort of carefully picking like a coloring of those nodes. Essentially, you color each one of those nodes, right? For example, this node in here corresponds to this node in the original tree, and you color this node by all this sort of transformations with like as many colors as there are different functions from, let's say, a state of the automaton to a state of automaton. So this is a pretty large constant, but it is a constant that only depends on the formula that we're considering and not on the particular size of the set A, which is sort of the thing that we have to be careful about in here. And so by labeling like each of those vertices by the sort of transformation on the automata state that each such selected collapsed subtree induces, we can sort of interpret this tree as a run of an automaton in here, right? And then basically the idea is that, well, what happens if you pick parameters? If you pick parameters, they will land in some of those subtrees, like maybe in here, right? But if they land in here, then what happens is that basically you change the labeling of this particular node, and this might influence sort of the final state in here, right? But how many labeling changes you get to do? You have to pick at most, you have to sort of, for each parameter, you have to pick a node of t prime, which you will change. So let's say this one, right? In here, I can pick arbitrary, right? I have one of the functions from like pairs of states to another state. I can pick one of those, but this is some constant number. And then I get the number of parameters of such choices, right? So all of this is raised to the power of y. But what this means is that, right, so how many of those choices we have? Well, we pick one of the nodes of t prime, we get some constants, which is sort of our alphabet size, which is the number of those transformations, and we raise this to the number of parameters, right? But in fact, this in here, the size of the tree has to be smaller than 2a, right? And so we can immediately see that this, in fact, turns out to be at most a to y times some constant c prime. And that basically shows that we have the desired VC density of the definable sets in those trees. All right, moving on to the lower bounds. So the construction that we actually use for this has been already observed in the related work of Grohe and Turin. So this is the VC dimension paper that I've mentioned before. And the idea here is kind of simple. So the idea here is that actually on grids, you can easily define sets of very high VC density, VC dimension, right? So what you do is you essentially like simulate a binary counter here on the right-hand side of your grid, and you basically select your set A to be sort of the bottom line of the grid, and each one of those, you basically select a formula which says something like x has to be on the left-hand side of the grid, and it is connected to all of those vertices that are on the bottom side of the grid if those sort of colorings are set. And you can actually produce those colorings purely using the MSO formulas. And so what this means is that, well, you can clearly see that because this is a binary counter, we sort of can exactly select every single subset of that particular set. And then sort of to finalize the proof, so they sort of noticed that this is a thing you can do, and they have used this to like prove that for the case of tree width, you can do this, but we have sort of completed the proof. We have written it up a little bit more carefully, I think. And so the idea is that, yeah, so we have sort of restated that using MSO2, you can actually define a grid structure inside the graph of sufficiently high tree width. And also using C2 MSO1, you can define a grid structure inside a graph of sufficiently high clique width. That depends on a lot of other related literature and vertex minors and is generally pretty involved in itself. But just composing those theorem, one can get those results. All right, so that is everything I have prepared for the day. Those are the sort of references that I have mentioned. Thank you for coming. If you have any questions, please come to our Q&A session. Thank you.